Okay, so continuing from Wednesday's lecture, we want to understand how to calculate limits. So limits are going to come up a couple times through this course, once now and then they'll come up again later this semester once we learn what's called L'Hopital's rule. We'll learn some even more advanced techniques for calculating limits. At the moment, how do we calculate limits? It's all going to be through specific algebraic techniques. So some of the examples, if you can't use algebraic techniques, you'll have to use calculator techniques. So there might be an example on the homework on the WebAssign, kind of like the examples we were doing on Wednesday, where you have to plug in some of the numbers. You have to get closer and closer values to the limiting x value that you want to compute the limit of, and then try to see if the function values, if the y values will converge. For most of these, or at least the ones that we're going to be doing today, any limits that we expect you to calculate by hand, especially the limits on an exam or quiz, you will be able to use these algebraic techniques. So again, it's a little bit of a review of pre-calculus, but we're starting to apply our pre-calculus techniques into some of these introductory calculus methods and techniques and topics. So the first thing we want to talk about are indeterminate forms, and we'll talk about these again later in the semester, and we will add to this list. So indeterminate forms. What is an indeterminate form? The root word is determine there, and it's indeterminate, meaning we cannot determine what this value should be. So these are going to come up in limits specifically. Remember, we mentioned this on Wednesday that if we try to plug in a specific value and we get an indeterminate form, it usually means there's a hole in the graph. If we're computing the limit, however, and we get an indeterminate form, it means we need more information. We need to manipulate our limit a little bit better to compute it. So we cannot determine. We need more info. / we need to adjust our techniques to determine the value. So what are indeterminate forms? The first three we're going to look at today are going to be 0 over 0, infinity over infinity, and infinity minus infinity. So the infinities we'll talk about a little bit. We'll actually have to talk about infinities again throughout this semester. Calculus is really a study of rates of change. It's a study of rates of growth. And this will be your first course where we really actually understand and try to take a mathematical approach to understanding what is infinity and how can we deal with different types of infinities and what are different types of infinities, at least from a calculus perspective. So we'll talk about these when we get there. Another way to think about indeterminate forms they occur when mathematical concepts clash with each other, clash or contradict. So if we take a look at these indeterminate forms, well, what's going on? We mentioned this 0 over 0 on Wednesday, right? Our idea is I can take any number, I can't divide it into nothing. If I have something, how do I divide it into nothing? I can't divide it into 0 groups. That doesn't make any sense. So typically a number divided by 0 is undefined. And in this course, actually, what we're going to start to talk about is that if we have a constant, say 1 or 2, if we divide that number by 0, it actually ends up being infinity or negative infinity. And we'll talk about when each of those occur. Conversely, if I have nothing, though, and I divide nothing into, if I have nothing and give it to 5 different people, everyone gets nothing. I can divide nothing and divide 0 by any number, and everyone gets 0. 0 divided by anything gets 0. So this number here should both be 0 and infinity. So these rules are kind of clashing. Likewise with infinity over infinity. Well, if I have a number, if I have anything, and I divide it into infinitely many groups, essentially the piece of that number that everyone's going to get is going to be infinitesimally small. It's going to be 0. On the other hand, if I have something that is infinitely large and divide it into 5 groups or some finite number of groups, well, then everyone's still going to have infinitely many into each group. So we have another clashing concepts here. Something that is infinitely big divided by something that is infinitely big, is it still infinity? Is it 0? Is it a finite number? And likewise with infinity minus infinity. If I have something that is infinitely bigger than everything and subtract off something that is also infinitely bigger than anything, what are we left with? These are kind of clashing concepts. And we'll see with limits today that sometimes we get finite values. There are other situations where we get infinite values or we'll get 0. So let's start with our basic techniques. How do we compute these and when do these indeterminate forms arise? So our basic algebra techniques, first thing you're going to want to try is always plug in the value. All right, let's specify. These are 4 limits. So the first thing you're always going to do with a limit is plug in the value, because most of the functions we're using for computing limits are going to be continuous functions. You do want to be careful with piecewise functions. So if you're looking at right and left-sided limits, if your function is a piecewise function, as we were drawing these types of graph on Wednesday, you want to be careful with one-sided and two-sided limits. So if I give you a piecewise function analytically, like listing out each of the pieces with the domain, you do want to be careful with just plugging in the value, especially if the value isn't going to match or is on the border between 2 different pieces. So pay attention to that. But if I just give you these limit as x approaches any number a of f of x, the first thing you're going to do is check f of a. And can we compute that value? If you can't, or if you do try to plug in that value and you get one of these indeterminate forms, then that tells you you need to use some of these algebraic techniques. So first technique is just basic factoring. So this is going to come up in rational expressions, factoring the numerator or denominator to see if you can simplify that function. So for example, let's suppose we want to compute the limit as x approaches -3 of x squared minus 9 over 2x squared plus 7x plus 3. So our first step is we want to plug it in. And so we'll get -3 squared minus 9. So that'll be 0 on the numerator. 2 times -3 squared plus 7 times -3 plus 3. And so check that real quick. And our denominator here will have 9 times 2 is 18. Minus 21 is -3 plus 3 gives us 0. So we get a 0 over 0. So this gives us an indeterminate form that tells us we need more information. How do we get more information? Well, anytime we have a rational function where the numerator and denominator are both polynomials, if I get 0 over 0, it means that I can actually factor out a factor of x minus a. In this case, it'll be x plus 3 from both the numerator and denominator. So the numerator, hopefully everyone's comfortable with factoring, x plus 3 times x minus 3. The denominator, we might have to do a little bit of work. And actually, I'm running out of space here. Maybe we'll just do this on a separate page. Let's do our scratch work here. How do we factor 2x squared plus 7x plus 3? We know we can factor out an x plus 3. So you can guess and check, or you can do factoring by grouping, whatever techniques you like to use to factor your quadratic polynomials. So let's go ahead and put x plus 3 here. And so we'll have 2x squared. That'll give us a 6x. We'll have to have a plus 1 there in order to factor that. So let me rewrite that on the next page. So factoring both the numerator and denominator, we've got x plus 3 times x minus 3. And then our denominator, 2x plus 1 times x plus 3. So this is exactly what's going on. Even though the function itself should be kept as the original function, graphically what's going on with this function is that it's going to look exactly like the function x minus 3 over 2x plus 1, except there's going to be a hole at x equals negative 3. So if we ignore the factor that creates that hole, both in the numerator and denominator, this is going to be the same as computing the limit as x going to minus 3 of our function x minus 3 over 2x plus 1. So this is going to be the general process. You can think of this as just kind of a loop. First step is plug in the value. If you get an indeterminate form, next step is do some sort of algebra to simplify the expression. Usually once you divide something out of a numerator and denominator or simplify that term, then go back and repeat. We've got a new function now, plug in that value again. And so as we plug in minus 3, what are we going to get? We're going to get negative 6 over negative 6 plus 1 will give us negative 5. So our limit will be 6/5. So that was our first algebraic technique. Other algebraic technique is going to be, let's see, multiplying by conjugate, common denominator. Let's do multiplying by the conjugate first. So this is going to hold for roots and trig functions. So what is multiplying by a conjugate going to do? We actually kind of have an example here with the last example. So when we say multiplying by a conjugate, it just means we have a sum of two different terms or a difference of two terms. And then what we're going to do is multiply by the opposite of that. So if I have a sum of two terms, we're going to multiply by the difference of those two terms. If we have a difference of two terms, we're going to multiply by the sum of those two terms. It essentially creates this difference of squares for us. And having a difference of squares is nice, especially if I have a square root. Then I can square that square root without adding in additional root terms. So let's do one example. Let's actually start with the example we were looking at on Wednesday. So on Wednesday, we computed this limit, or we approximated this limit or guessed this limit by using a table. We had 3x minus 12 over root x minus 2. Again, our first step, when we plug in 4, gives us a 0 over 0. So we get our indeterminate form. And I will remind you guys, do be careful with that. I mean, once we get in the habit of these limits, especially with this section, and as we use limits again and throughout the course, it starts to become a little habitual to just start using some of these advanced techniques. But there are curveballs at you where if you get like 1 divided by 0, undefined. If you get 0 divided by 5, 0. So you don't need to do anything after that. So careful with stuff like that. We do get an indeterminate form though, which tells us move on to the next step, do some algebra and try to simplify this. So we want to apply the same type of algebra, except now, you know, factoring is kind of the same concept that's going on here, except it's a little bit harder to factor a square root type of function. So what we're going to do is multiply by our conjugate. We're going to take advantage of this difference of squares to get rid of the square root in our denominator. So if I multiply and divide by square root of x plus 2, right, we have square root of x minus 2, multiply by our conjugate just means changing that minus to a sum. So difference of terms, multiply by the sum of the terms. And so nicely enough, this is going to make our denominator a difference of squares. We'll have square root of x squared gives us x, and then minus 4. Our numerator, I'm actually going to keep factored, especially with this technique. Wherever the square root appears, if it's in the numerator versus the denominator, keep the other side factored. We like foiling out our denominator because that's where the square root was. This technique applies to specifically get rid of that square root. And what we're going to look for to see if it will cancel with something in the numerator. So I'm actually going to factor this a little bit more. I'm going to pull out that factor of 3 specifically so we get this x minus 4, but the square root of x plus 2, I'm just going to keep factored. We're not going to multiply or distribute that through. And now we can see we have this term of x minus 4, both in the numerator and denominator. And so now what we want to do is compute the limit of what remains. So 3 times square root of x plus 2. And our denominator is just 1. So I'm not even going to write it there. So notice again, we have similar process. We apply an algebraic technique. We look for terms to divide. Once the terms divide, we've simplified things, and then we plug in the limit again. So this is going to be 3 times square root of 4 when we plug it in as 2. And we see that the limit is 12, which is what we were getting at on Wednesday. So our tabular approximation confers with our actual mathematical techniques. The other time this multiplying by a conjugate is going to come up is with trig. So why does it come up with trig? It comes up with square roots because we got to get rid of that square root. It's not easy to factor and look at these square roots in a different way. The best way to really look at them in a different way is to really kind of shuffle them around is what we did. If you kind of notice what the result was, we just manipulated this expression so that the square root is now on the numerator or vice versa. And because we had that conjugate in there, it plays nicely with that limit we plug in. So squaring our square roots is nice, but sometimes with trig functions, we have all these sum of squares, difference of squares, Pythagorean identities. So if you remember that from the first couple days, our refresher on trig, we have nice trig laws like 1 minus sine squared is cosine squared. So we can take a difference of terms, or sometimes a sum of terms that are squared, and turn it into a single term, which can help us simplify our expressions. See, I believe I have an example here. Yeah. Let's do something like we want to compute the limit as theta goes to 0 of cosine theta minus 1 over sine theta. So our first step, when we plug in our limit, cosine of 0 is 1, sine of 0 is 0. So we get 0 over 0, which tells us we need to do some algebra or some trig techniques. So of course, factoring isn't going to help us. The only thing we can really do is use this conjugate technique. We like to take advantage of 1 minus cosine squared and 1 minus sine squared, our Pythagorean identities. And we have something like a cosine squared a cosine minus 1. If it were cosine squared, then we could use our trig identities. So what we're going to do is multiply and divide by our conjugate, difference of terms. Let's go ahead and multiply by the sum of those terms. So cosine plus 1 divided by itself. Mind your parentheses. This is a common mistake, especially if this one's not too bad because we just have a single term in the denominator. But if you did need to distribute this, I would say don't distribute it at first. See if you can look to things to factor and cancel. There might appear situations where you do need to distribute things. So mind the parentheses if you do have to distribute. But again, always look to see if you can factor and cancel things out first. And now when we multiply our trig terms out, so we'll have cosine squared theta minus 1 over sine theta. And again, I'm going to keep this factored at first to see if we can look for things to divide. Now with trig, we've got this extra step. Up here, we maybe had to do one extra factoring step, but hopefully the division was fairly straightforward. Here, we do have to apply perhaps some extra techniques because we do have our special class of functions, our trig functions. We might want to look to use a trig identity. So cosine squared minus 1 is negative of 1 minus cosine squared. So this is going to be, and let me go ahead and keep writing the limit. I don't know how much sticklers the TAs are going to be. We should write the limit in front of each of these. I don't know how rigorous they need to be. I would say try to write the limit term right before you're writing your conclusion. So this is going to be minus sine of theta over sine of theta times the quantity cosine theta plus 1. And so we see, using our trig identity, now we can divide. And when we divide and compute our limit, I wrote that backwards. Sorry, that should be a 0. Ignore that theta. We'll have negative 1 over cosine theta plus 1. And so we'll get a negative 1/2 when we plug in those values. Questions on that one? Negative sine squared, it would be negative sine squared. I did miss that. Thank you. So if it's negative sine squared, we did our computation wrong. Let me get another page here. So when we have our negative sine squared, that gives us an extra factor of sine in the numerator. So correcting ourselves, what are we going to get? So we will divide out one factor of sine in the numerator. So we will have our limit as theta goes to 0 of negative sine theta over cosine plus 1, cosine theta plus 1. And then when we plug it in, we'll have 0 over 2. So we'll get 0. as our limit. Thank you. Okay, last technique is going to just be adding fractions. So what do you do when you're adding fractions? Common denominator. So this can come up in a couple different ways, and this is actually going to come up with our infinity over infinity. So I guess another note. Excuse me, infinity minus infinity. So let's do a couple examples. Let's actually start off with a basic one. So something that'll give us a 0 over 0. The limit as x goes to positive 3 of, let's say, 2/3 minus 2 over x divided by 3 minus x. So notice we have a rational functions inside of a rational expression. So we have this sort of, I call them compound fractions. We've got a fractional expression within a bigger fractional expression. So within our numerator, if we plug in our 3, what's going to happen? We'll have 2/3 minus 2/3 divided by 3 minus 0. So we still get our 0 over 0. But again, because we're not working with polynomials, it's going to be a little hard to factor. Our denominator, our big denominator, 3 minus x, is a polynomial, but it's a linear polynomial. Can't really factor it. So what would we do up here? Well, we can't quite factor it. So pretty much do the only thing you can do whenever you're adding and subtracting fractions, and that is find a common denominator. So let's just work with the numerator first if you'd like. So maybe a little scratch work. So if we have 2/3 minus 2 over x, what's our common denominator going to be? 3x. So we'll have 2x over 3x minus 6 over 3x. So multiply by 3 over 3, multiply by x over x. And I guess if you'd like, we can write in those steps. So we just multiplied x over x times 3 over 3. And now we have a common denominator. And so we'll get 2x minus 6 over 3x. The other thing that I think is helpful for compound fractions is write the big denominator as a reciprocal. So really what we're trying to compute here to make it a little more visually better to see what our mathematical steps are. Our numerator, we simplified or adjusted to write it as 2x minus 6 over 3x. Dividing by 3 minus x is same thing as multiplying by 1 over 3 minus x. So I don't like the way those look. I think it's harder to see the math, and it's really easy to confuse and flip things between the fractions. So I just write that as 1 over 3 minus x. And now what are we looking to do? We're going to look for simplifying. We're going to look for dividing and canceling out factors. So our numerator, we can factor out our 2 from that 2x minus 6. We've got a 3x in the denominator, and I'm going to go ahead and just throw this factor of 3 minus x with that denominator. And so those two terms will divide. Be careful, though. We are left with an extra factor of minus 1. Which you can put in the numerator or denominator or keep it out front. So we've got the limit as x goes to 3 of minus 2 over 3x. And now when we plug in our 3, right, we've made our cancellation. plug in our value again and repeat the process. So we plug in our 3 and we'll get minus 2 over 9. Other questions or questions on that guy? So the other technique, or the other time that adding fractions is going to come up, is when we don't have a fraction within a fraction. We're just subtracting fractions. So since you're in calculus, note, from now on, you want to think of as infinity or minus infinity. Sometimes there's a specific one you can choose. Sometimes there's not. And when I say a C, is just some constant that is non-zero. So C is going to be a number non-zero. 1, 2, 3, minus 3 halves, anything like that. So if it's constant over 0, think of it as infinity or minus infinity. And then there are certain situations, which we will get to, that you want to choose one specific, but it is a type of infinity. So let's do another example. If we do something like the limit as x goes to 0 of 1 over x minus 1 over x squared plus x. When we plug in our 0 now, what we're going to get is 1 over 0 minus 1 over 0. And again, you want to think of that as infinity minus infinity. It's a mathematical contradiction. Saying I have something infinitely big, but I'm also taking away something infinitely big. What are we even left with? It's hard to think about. It could still be infinite. It could be finite. It could be nothing. It could be negative infinity. So it's indeterminate. We need more information. And that's really what the signal is. It's all it kind of tells us, is that we need more information. So how do we get that more information? Well, we've got two fractions and we're trying to subtract them. The only thing we can do is find a common denominator. So let's just go ahead and do that. Our limit as x goes to 0 of, so what is our common denominator? Maybe we can do another little scratch work box. We've got 1 over x minus 1 over x times x plus 1. So I'm factoring this denominator. So we want to multiply this term times x plus 1 over itself. And then this term has already this factor of x. So there's nothing we need to change in terms of the second denominator. So it's still going to remain as 1 over x times x plus 1. I kept that denominator factored. I don't feel like we want to distribute it again. We always want to look to factor things. In almost all of these indeterminate forms, we want to look to factor and cancel something eventually. So as soon as you factor one thing, not needed to redistribute it, at least not at first. You might have to do it down the line. I would say general just algebra tips, keep it factored until you've run out of other options. So our numerator, let's go ahead and simplify that. Since I have an x plus 1 minus 1, we just get an x left in the numerator. And our denominator, since we've kept it factored, we see we have that factor of x. We'll divide those out. And so now computing this limit is going to be the same as computing the limit of 1 over x plus 1. And when we plug in 0 now, we just get 1. Any questions? So we only have 2 minutes. Let's see. So we actually, those are the bulk of the techniques. Let's real quick just mention a few things. Look over the properties of limits. So this is going to be in the book. And what do I mean by this? This is going to be things that are in terms of adding and subtracting. So like if I have a limit as x goes to a of 2 different functions, if the limits exist, then I can compute the limits separately and add them. So I can compute the limit of x first and then add it to the limit of g. So be careful with this. It does imply that the limits have to exist. So like with this one, if I tried to do these separately and compute this limit first and then add it or subtract it from this limit, well, it wouldn't work because this limit goes to infinity, which is a does not exist. And so because both of the limits do not exist separately, we've got to be careful with this sum and addition formula. So I'll put that as plus minus actually. Same thing applies for scalar multiplication, for multiplying and dividing functions, and for exponentiating functions, at least to a positive exponent. All those rules apply, but be careful. It does require that the limits exist first before you perform the operations. The other thing we will need to talk about is the squeeze theorem. So maybe I do want to actually talk about that. And since we're out of time, we'll have to talk about it on Monday. If you would like, actually, maybe I'll mention it. You guys might have a WebAssign on it. So real quick, the squeeze theorem says, if we are looking at 3 limits, limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x is less than or equal to the limit as x goes to a of h of x. So if we know f of x is less than g of x is less than h of x, and then we want to compute the limit at a specific point of those, if the limit of f of x is equal to the limit of h of x, then g of x also has to be that limit. So our example is something like the limit as x goes to 0 of x squared sine of x. This is going to come up quite a bit with trig, especially sines and cosines, because sines and cosines oscillate. So what's going on as x goes to 0? Sorry, sine of 1 over x. So we looked at this, sorry, that's not on the page. We looked at a limit on Wednesday of sine of something like 1 over x. It was like a constant over x, and that limit doesn't exist. However, we can bound this. I know that sine, no matter what the input of sine is going to be bounded by 1 and -1. So it's bounded above by 1, bounded below by -1. So this is always going to be less than or equal to x squared, and it's always going to be bigger than or equal to -x squared. So since sine is going to be less than 1, we replace sine with 1, and we're left with that x squared. Sine is going to be bigger than negative 1. So this expression will always be bigger than minus x squared. And if we compute the limits on the right and left, we can conclude that this limit in the middle has to be 0. The last thing, we won't be able to do this until later this semester, but you might have to use it for homework, is that we know that the limit of sine theta over theta is going to be 1. So if you know this fact, you can use this in some of these sums and difference limit properties to solve certain problems. Any questions? Do it at the top. Everyone got all the notes? So have a great weekend. I can put up the notes again if anyone needs them. I'm going to go ahead and stop the recording, though. I'll see you guys in person on Monday.